On the one hand, properties improve with density. On the other hand, properties reduce with grain coarsening. And so you got to find a balance. It's an optimization problem. Of course, if you compact the material and you sinter it, then you can reduce the porosity, you can increase the heat transport, providing pressure from different directions, especially in a mold, provides shape control. So hot pressing, for instance. You can also reduce dimensional change. You can improve properties, and you can increase the final density by promoting plastic flow and so on. So accordingly, you can see the sintering variables include various material compositions, right? So alloys, additives, in terms of sintering aids, pre-alloyed powders versus mixed powders, powder shape, powder size, and then when the powder is put together into a shape, so the density of that material to start out with, and any uniformity or non-uniformity of that density. Right. So this is what you start out as a shaped part with the first four parameters, and then things like heating rate, temperature, time, cooling rate are important. And then we'll see that depending upon the powder chemistry, whether it's an oxidizing atmosphere, reducing atmosphere, inert atmosphere, that would matter. The presence of any carbon and moisture can also make a big difference. So the dew point and carbon potential come into factor as well for certain compositions. Typical atmospheres include an inert atmosphere. Nitrogen or argon are good examples. Reducing atmosphere, it could be hydrogen or natural gas based, or it could be dissociated ammonia, so mixture of nitrogen and hydrogen. Or you could have vacuum as typical sintering atmospheres. And depending upon the reactivity of the powder, the presence of oxides, and so on, we might choose one or another material. So for instance, if you're sintering aluminum oxide, you can sinter it in air. You don't have to worry about oxidation. You don't have to worry about getting rid of the surface oxide layer. But if you are sintering a stainless steel, for instance, it'll have an oxide layer. You might want to reduce it under hydrogen, or you want to be able to sinter it in vacuum so that you can minimize the amount of oxidation at higher temperatures. If you're sintering silicon nitride or aluminum nitride, you want to sinter it in nitrogen or argon. Okay. In terms of the furnace in which you will sinter the material, you have either a batch furnace, right? So it's like your kitchen oven. Take a tray of cookies, put them in. After a certain time, at a temperature, you take them out. That's periodic. Alternatively, for productions in high volume, you would opt to a continuous method, right? Where you can control the heating path, you can control the overall dwell time at a given temperature range. You can control the atmosphere. So this is an example of a typical batch furnace. Pretty much practically all of vacuum sintering is done in a batch furnace. There are a few innovations that allow it to be semi-continuous, but usually you want to just be in a batch furnace, right? And so you have some controls. You have this big chamber over here. Sintering is typically done in radiation heat. Here's an example of what the inside of that chamber looks like in a photograph. These batch furnaces can also be modified to operate under inert gas or under hydrogen or something like that. For continuous production, you want to be able to keep loading parts at one end that need to be sintered, and there's a moving belt that goes around, and there are constantly emerging parts from that furnace. And so this allows you to program a certain production rate where the preheating, the heating, and the cooling down is all dialed into this overall cycle. Many of these belts typically are made by a high temperature steel, and so for at least ferrous parts, typically the parts made in press and sinter, there's an upper limit to how high these belt furnaces can go. It's typically about 1150 degrees C. And so that limits the materials that you can sinter, and it also limits the density you can and properties you can obtain. Still, you can get a throughput of typically something like about 150 to 300 kilograms an hour. Some are a little bit lower, but typically this is what you can achieve. In some cases, instead of having a high temperature steel or stainless steel belt elements, you can have ceramics, silicon carbide being very common. You can occasionally have alumina and silicon nitride as well. That will allow you to go to maximum operating temperatures of 1500 degrees C. In some cases, we've seen that you can go up to 2000 degrees C or 2200 degrees C with ceramic belt furnaces. KYK being one example of that. A visual of what one of the belt furnaces typically looks like over here, and often used for press and sinter operations. Variations of that theme where you can get past that temperature limit by avoiding moving components in the high temperature zone is a pusher furnace. So you have a rod that can be pushed through this mechanical elements that are external to the furnace. So there are a series of ceramic or refractory bricks on which parts are placed, and in the hot zone, this rod that is pushing this material moves the bricks along a surface, and then parts come out at the end after cooling. You can have different heating zones depending upon the pushing speed. You can end up having different kinds of dwell times at different temperature zones. You can control the sintering time and at various temperatures. So think of it as a situation where every time a part is removed from here, another tray of bricks is placed at the entrance. And so this will allow for a continuous operation. Because there are no moving parts inside the hot region per se, that are key to pushing the parts along, it's just brick to brick motion. You can get to higher temperatures and can go up to 1800 degrees C in some of these things quite easily. And so for injection molding, where you need much higher densification than press and sinter, a lot of the time you will end up using a pusher furnace for production reasons. This is an example of what the pusher furnace looks like. And one size, they can go from a benchtop unit for very small production volumes to something that can a few hundred meters long. And you can get capacities that reach up to 400 kilograms per hour. So to summarize, sintering depends on many factors. Particle size is one of them, and its curvature. Green density, initial density makes a big difference. The final density makes a big difference. And so the distortion and dimensional change that occurs and translating from this initial state to the final state needs to be controlled. Depends upon the powder composition, the presence of any alloying agents or sintering aids. There are a lot of furnace options